So in the late 1800s, there were scientists working on developing the periodic table, and the scientist that gets the credit for her developing it is actually Dmitri Mendeleev, who arranged the periodic table, and he left some blank spots in his table. And this is important because essentially what he did was he predicted elements that had not been discovered yet. So sure enough, the elements that Mendeleev predicted were actually discovered later on. These elements were right under aluminum and silicon. And the reason that's important is because he had left those spots empty, and later on they were discovered, and these are now gallium and germanium, and they have properties that are similar to aluminum and silicon, respective to the families that they're in. The whole point of the periodic table is so that you don't have to memorize each individual element. You can look at a group, we're going to talk about what those are, and you can predict properties based off of that group. So this meme makes me laugh because he probably looks at chemistry teachers who make you memorize the periodic table. But I won't ever make you memorize the periodic table, don't worry. So the periodic table is divided into columns and rows. Periods are the horizontal rows. So as you go along each period on the periodic table, you can see that atomic size is increasing and also atomic number. For groups, these are the vertical columns. Within these columns, we call them families very often. I like to call them families. And we call them families because these elements in the vertical columns will act very similar to each other. There are a total of 18 groups and 7 periods. I like to stick to the 1 through 18 numbering system. There is an A and B grouping system. We'll just stick with 1 through 18 for this class. And there are 3 different types of elements in the periodic table: metals, nonmetals, and metalloids. So some properties of the different types of elements. So metals are shiny, malleable, good conductors of heat. You guys know how metals are. You see those in your daily life pretty often. Malleable, in case you don't know what that means, it means you can like bend it or you can shape it into a form pretty easily. Nonmetals are completely the opposite. They're dull, they're bad conductors of heat and electricity, and metalloids are somewhere in the middle. So here you can see the different classifications. Metals are this light yellow, and they take up most of the periodic table. In between metals and nonmetals is this little staircase, and that's where the metalloids are. So they're very it's very certain ones. They're on this staircase. And then nonmetals are on your right-hand side of the periodic table, and also hydrogen. It's kind of an outlier, but it's there. So we also categorize elements either as main group elements or as transition metals. Main group elements, you can predict properties about them based on where they are in the periodic table. And this has to do with their families. Now, transition metals, the properties, you really can't predict them, honestly. They're varying in charges and varying in a lot of different things. But main groups, you can look at the group that they're in and you can say, okay, that element will behave in XYZ. So in addition to classifying elements either as main group elements or as transition metals, which you can see here, we also have names for a lot of the main group elements. So the ones that I want you to know, and the reason that this is important is because later on I will refer to a lot of these groups of elements through their common group names, and I want you to know that, and plus it's easier. So group 1 is the alkali metals. Group 2 are the alkaline earth metals. We know that these are the transition metals, and then the other 2 groups that I want you to know is the halogens and the noble gases. So these are some properties of these main group families. So the noble gases, they're very unreactive. They like to stay how they are. They don't like to combine with other elements. An example is helium that you use to fill balloons. The alkali and alkaline earth metals are pretty reactive, and alkali are actually more reactive, but pretty much if you have solids of these metals and you throw them in water, it will explode very violently. So go check out a YouTube video, just type in sodium reacting with water, and you'll have fun watching that. And then we have the halogens. They are pretty reactive as well. In fact, they're so reactive that in nature you don't find them on their own, like in their elemental form. You'll find that they have already reacted and they form salts, which we will talk about later. So we can actually also predict charges on the periodic table based on groups. First and foremost, I want you to understand that main group metals, which are the metals in these two groups, remember transition metals are in the center, main group metals are right here. And then we have main group nonmetals. So Mg is main group, transition metals in the center. These are metals, these are nonmetals. Main group metals tend to lose electrons. So these over here will become positively charged cations, versus main group nonmetals will become negatively charged. So I'll circle that right here. And both of these do this so that they can look electron-wise like their nearest noble gas. So everybody wants to look like a noble gas in terms of their electrons. So keep that in mind. So I think this is the way to remember the charges on groups in the periodic table the easiest way. Group 1 is positive 1, group 2 is positive 2. You skip the transition metals. Group 13 is positive 3. From there on, carbons group. So carbons is a special group. That one can technically be either plus 4 or minus 4, so that's your dividing line. From there on, everything else is negative. So nitrogen's group is negative 3. Oxygen's group is negative 2. The halogens will form a negative 1 charge, and then the noble gases don't form any charge. The reason that these elements, these groups form these charges is because whenever they either lose electrons, so anything positive means that they have lost electrons, anything negative means that they have gained electrons. When fluorine gains 1 electron, its electrons look like neons. When oxygen gains 2 electrons, its electrons look like neons. When aluminum loses 3 electrons, so 1, 2, 3, its electrons will look like neons. So this is what elements do. These are the charges that these groups, these entire groups, will typically form. So just memorize it this way. Know that there's that dividing line right there with carbon, and that to the left of that line is positive, to the right of that line is negatively charged ions. So now we're actually going to switch gears a little bit and talk about bonding, and later on we'll talk about nomenclature. So there's two types of bonding. The first is ionic bonding. Ionic bonding occurs when electrons are transferred from one element to another. An ionic compound is a compound that has ionic bonds within it. And generally, ionic bonds form between a nonmetal and a metal. So this is very important in order for you to be able to recognize what type of bond is occurring in a compound. And also, from then on, if you need to name that compound, you will know how to name that compound. An example of this is table salt, so sodium chloride. Sodium's a metal and chloride is a nonmetal. This is how it looks atomically. This is how it's arranged. Here we have another example. This is actually bleach. And the main ingredient, oh, not the main ingredient, but the active ingredient that acts as the oxidizing agent in bleach is sodium hypochlorite. Sodium is a metal and hypochlorite is a nonmetal polyatomic ion. So this is another example of an ionic compound. So the other type of bonding is covalent bonding, and this occurs when atoms share electrons in comparison to ionic bonding, where one or more electrons are completely transferred to another atom. Whenever compounds have covalent bonds, they're called molecular compounds, and generally you will see covalent bonds form between nonmetals. So when you have one nonmetal, another nonmetal, that means it has covalent bonds, and that means you call it a molecular compound. A good example is propane, which you use to grill stuff up, to grill those burgers up. Hopefully you guys have seen King of the Hill. Propane is composed of carbon and hydrogen. It's C3H8, And for salts, so for ionic compounds, I'm sorry, what you would generally see is that it'll be a crystalline solid, but for molecular compounds, you'll see liquids, you'll see gases like propane, you'll see solids, many different types of forms in comparison to those ionic compounds. So compounds can be demonstrated in several different ways. The majority that you'll see is through the molecular formula, which shows the chemical symbols of the types of atoms. So for example, this compound is called methane and it has carbon and hydrogen. And these symbols will be followed by the subscripts to show the number of atoms in that molecule. So one is typically omitted, so that's why you don't have anything right there for that carbon. There's just one. For hydrogen, you have four. You can also demonstrate molecular formulas through structural formulas. So this actually shows how the atoms are connected, and these little lines are called bonds, which you'll learn about later on in the semester. You'll also see these models, which are either space filling models or just molecular models, like how they look in 3D space. This black atom is demonstrating the carbon, and then you have your hydrogens. So I also want to point out or remind you about the fact that there are monatomic atoms versus diatomic molecules. So you guys know the diatomic molecules have no fear of ice cold beer. Monatomic atoms exist on their own, for example, noble gases and, for example, many metals. You also have polyatomic molecules, which is, for example, sulfur, which is S8. Now, I want to point out these differences between coefficients and subscripts. So this right here is demonstrating a monatomic atom, one hydrogen atom. You only have one, that's all it's showing. This right here with the number in front of the symbol is demonstrating that you have two separate monatomic atoms. This right here, since you have that subscript, that means that you have two atoms bonded together. So this is one hydrogen molecule. This right here is, I guess, the most important one because it's showing you have two separate hydrogen molecules. So the subscript tells you that's a molecule. This coefficient in front tells you there's two different units of those. So now we're going to predict the types of bonds within given formulas of different compounds. Now all you have to do is look at whether it's a nonmetal plus a metal or nonmetal plus nonmetal. If it's nonmetal plus metal, that's ionic. If it's nonmetal and nonmetal, it's a covalent compound. I was about to say molecular. It's a molecular compound, but it has covalent bonds within it. Ionic bonds, ionic compounds, that one's the same. So sodium and iodine. So hopefully you have your periodic table next to you, or hopefully you have it pulled up on your phone or something. I already know what these are, that's why I'm just going based off memory. Sodium is a metal, iodine is a nonmetal. That means it's ionic. Hydrogen is a nonmetal. Nonmetal. That means this has covalent bonds within it. Carbon, hydrogen, and chlorine are all nonmetals, so that means these all are covalent bonds. Calcium is a metal. Carbon and oxygen are both nonmetals, so that means this is ionic. Now, between this, or inside of this, actually you have a polyatomic ion. Within that polyatomic ion, you have covalent bonds, which you'll learn about in a second when we start talking about naming. Now, again, we have the same situation here where we have a polyatomic ion that has covalent bonds within it, but as a whole, it's an ionic compound because cobalt is a transition metal.